In contrast to my talk earlier this morning, I get to report on a little bit of a realization of a dream rather than just living in dream world. And I'll speak on behalf of Binping Zhao, who wasn't able to come, but this is functioning as his dissertation project. Okay, there has at the Jefferson Lab been under conceptual development, even mentioned in this room 4 years ago, the development of a system for measuring the surface impedance of small samples at 7.5 gigahertz. It's in some ways very complementary to the last talk. This is a sapphire loaded to E0 and 1 niobium cavity. We make calorimetric measurements of surface resistance and changes in penetration depth as a function of temperature and peak field. And the sampled area by the RF is less than 1 square centimeter. Okay, in the middle of a 50 millimeter disc, flat disc. We've recently completed the initial commissioning runs using a niobium sample as a reference, and it's a system that we contend is very much ready for investigating higher TC materials. Welcome all comers. I would love to have an MGB2 sample. Okay, and then there's next generation. There's always what's coming next. Right? We've mentioned several times today the interest in trying to build the correlation between thin film morphology and obtained RF performance, and then upstream of that, the creation techniques for creating such films in a closed loop so that we can actually converge. So our solution to this is this SIC system. We call it surface impedance characterization. Okay, a little orientation. You might have seen this before. This is a niobium cavity. This is actually reactor-grade niobium. Sapphire loading. The main interest is to push to small scale. So you need the smallest sample as possible in order to better accommodate creation and analysis. There's a double choke joint here, so this is actually a non-contacting TE011 modes formed here. The fields are concentrated at this interface. The sample is the green piece here. There's a separated calorimeter here, so this is non-contacting. There's an intermediate controlled temperature ring, so cooling of the sample is via conduction path to here. This sits in liquid helium bath. The niobium sits in the liquid helium bath, so we're able to independently control and regulate the sample temperature independent of the niobium and the bath temperature, okay, via heater here and temperatures. Okay, variable coupling on the input and on the output we have been, but recently we're transitioning to a fixed coupling there. Okay, trying to understand, so the work that I want to report on is the characterization of the system and basically the steps we went through to qualify it, understanding what it really measures so that it becomes a useful instrument for unknowns. The surface impedance has a real part and imaginary part. We need to know the calibration of this constant here and this constant here. Okay, by microwave studio analysis, the sensitivity, this is 30 hertz per nanometer. It's frequency sensitivity of the gap and or the penetration of RF into the field. These two terms, this is stored energy. Our peak field is a function of stored energy. One of the things we challenged Binping to do is to give us confidence, because the mode structure at 7.5 gigahertz is pretty rich. We want to make sure we're making measurements on the right mode. So this is this M factor want to demonstrate that as a function of increasing the gap, we observe the frequency change we expect from simulation. And he did this both at room temperature and at 4 Kelvin. Give us confidence that we're looking at the right mode. Okay. Another factor we want to consider and understand is the working dynamic range of the calorimeter. Because of the significant thermal impedance between the sample and the bath, you're constrained by how much heat you can dissipate for your sample measurement. So this is with a measurement with no RF heat on the sample, but just heater heat. Milliwatts, 10 milliwatts on the sample. This is the temperature of the sample in equilibrium. So the measurements are done by a heat substitution method. So if we want to make a measurement, for example, at 4 Kelvin, you run the heater at that rate, then run RF and regulate for controlled temperature by backing off in the heater heat, thus measuring the RF supply dissipation on the sample. Okay, so this one is with the bath temperature at 2 Kelvin. We can take the bath temperature to 1.8, sometimes a little bit lower if we work at it. Okay, so for terms of sensitivity, roughly 1 millikelvin temperature rise corresponds to 1 microwatt dissipation on the sample at 2K, 6 microwatts at 9K. So the calorimeter gives us a lot of sensitivity. And then we wanted to make sure that we had a good thermal bond of the sample to the sample stage, that we're actually measuring the sample, understand what the sample temperature is as a function of temperature, and this was 1 millikelvin. So confidence within 2 millikelvin that we know what the sample temperature is. He had demonstrated. Now, this is a figure that we try to capture what the working range is of the SiC system, where this is surface impedance in nano-ohms. This is peak magnetic field, millitesla. Okay, and this is temperature. So if we want to make a measurement at 2 Kelvin, this is a working range. If you want to make a measurement at 3 Kelvin, you could extend up to here. We're constrained by the limitations of the calorimeter I mentioned, as well as our ability to build up field in the resonance. That's constrained by our available RF power and the Q of the resonator, which now is only about 10 to the 7. Okay? That's what limits us to this peak field right here. Now, he included on here some nice other materials of interest that we would love to be able to explore. So right now we're living with a 22-watt TWT. If you have one at 7.5 gigahertz, if you have a higher power source, we'd love to talk to you. CW. These are CW measurements, not pulsed. And if you have some niobium nitride source samples that are 50 millimeter diameter, we'd love to talk to you. If you have a magnesium diboride sample that you'd like to actually measure the surface impedance, we have a place for it. Now, we wanted to qualify the system by using niobium. The physical structure now requires for best match, assumes a copper substrate, because we're aiming at deposited films on copper. So the best thermal contraction interface is copper to copper. So we took Ben Ping took a thin sheet of niobium and brazed it to copper, kept it flat, and that's what we measure the surface impedance as a function of temperature with here. Okay? The blue curve is a BCS fit. Two arrangement. This is TC over T. Okay. And we also measure the change in London penetration or penetration depth as a function of temperature. This is a BCS fit to the measurements from just under TC down to about 6.5 Kelvin. That's from frequency change of the resonance. And these are the BCS fit parameters reflected in the two previous curves. With the residual resistance fairly high, but we attribute to this has been a pretty much abused niobium sample from the brazed environment. So having attained a nice niobium fit to come up with very reasonable niobium parameters other than the residual resistance, you can say we've commissioned the system. It's now ready for business. The resolution can be as low as 1 nano-ohm with 5 millitesla peak field, higher at higher fields. We can reach now 14 millitesla, limited, as I mentioned, by the Q of the cavity and the available RF power. And since the sample temperature is independent of the cavity and the helium is constrained by the helium bath, but independent of it because of the calorimeter arrangement, the system is ideal and ready for exploring higher TC candidate films. Any questions? And this is future, but the talk is on commissioning, not future.